Logarithmic differentiation is a method that may make finding the derivative of a function much simpler than if we were just following the standard differentiation rules. So, for example, if you're supposed to find dy by dx and y is the square root of x plus 3 raised to the power of 5 divided by x squared plus 2 times 3x minus 1 in brackets. Now we can of course use the chain rule because we have a square root and then a function inside. We can use it a second time. We have x plus 3 raised to the power of 5. I can also see a quotient in there, and I can see a product if you look at the denominator, just down here. So we can apply all of these, and it might get quite complex. If we have this kind of situation where we're supposed to use multiple times the product rule, the chain rule, or the quotient rule, or another case, if the independent variable is in the base and the exponent. For example, if we had something like x plus 1 in brackets raised to the power of x, we can use logarithmic differentiation. So what is that? Now let's start with dln by dx. Well, we can easily find that because according to the chain rule, this is just dln by dy, dy by dx. Now dln by dy is of course just 1 over y. So we can now rearrange this and we can write dy by dx as y times dln by dx. So that means that the derivative, if we're looking back at our question up here, dy by dx can just be written as y times dln by dx. So if we can find dln y, differentiate with respect to x, and multiply by y, we have our derivative. Let's do it with this example. Find ln y. Now ln y is just natural logarithm of y, and y was the square root. So we now have ln y is ln of the square root of this ratio. Now let's simplify this, and this is where you can see that using logarithms can be very powerful, because we have certain laws that apply to logarithms. In this case, we have the logarithm of a square root of a function. Now that means we have the function raised to the power of a half inside the logarithm. And that means we can write it as a half times the logarithm of what was inside the square root. Now if you look at what we have inside the logarithm, I can see a ratio here. And I can also see a product if you look at the denominator. So we can write this as a half times ln of the numerator minus ln of the first factor in the denominator minus ln of the second factor in the denominator. And of course I can go one more step, and I can also simplify this first term, because we have x plus 3 raised to the power of 5, so I can take the 5 to the front and we get 5 over 2 ln x plus 3, and I've just multiplied the half inside, and we now have minus a half ln of the second term and minus a half ln of the third. Now this is a much simpler representation than what we started with. Much simpler and much easier to differentiate. Because now, as we said before, dy by dx is y times dln by dx. We have ln y. Let's find dln by dx and multiply by y. So first of all, y was just this square root here, so I've just repeated it. dln by dx is just the derivative of this with respect to x. And as it turns out, it's just this. The derivative of 5 on 2 ln x plus 3 is of course 5 divided by 2 times x plus 3. And we do the same for the other two terms. And here we are. We didn't have to apply the chain rule, the product rule, and the quotient rule a number of times. This was much simpler. And this is where the power of logarithmic differentiation lies.